This conference will now be recorded.
So welcome everyone to another OCP session. This will be actually the 69th session. So today we have Dr. Will Myrick. So Dr. Myrick is currently a Chief Engineering in the Mission Solution Group, MSG, at ENSCO. Yeah, I really practiced that, but it didn't go through, I guess. exploring a variety of assured positioning, navigation, and timing A-PNT research topics. He leverages his 20 years of experience in one low-cost COTS, which basically stands for component off the shelf, software
Yep.
defined radios, SDRs, to subspace digital signal processing, and 3 distributed sensor fusion to provide a unique set of experiences and perspectives as a subject matter expert for A-PNT. He is involved with a variety of A-PNT internal research and development efforts at ENSCO related to building inexpensive COTS-based A-PNT systems. Dr. Myrick holds Master of Science and PhD degree in electrical engineering from Purdue University and Bachelor of Science in electronics engineering from Norfolk State University. It's interesting, Purdue University, we had Dana Weinstein also 2 weeks ago talking about her research. Anyways, so
Very cool.
with no further ado, the floor is yours, Will.
All right. Well, thank you very much. Definitely appreciate this opportunity to talk with you today, Ahmed, as well as the team of timing experts. What I want to do today is just pretty much give you an overview of some of the things that I'm working on at ENSCO. We leverage a lot of different kind of COTS technologies, and I'm always curious of trying to figure out how can I take COTS technology and leverage it to support some of the things that we're focused on in terms of just timing and timing measurements. And in particular, for this presentation, I'm going to be talking about jitter. One of the things that I've noticed over the years is a lot of times it's hard to find equipment when you need it in terms of making measurements. And since I'm a maker by heart, I'm always looking for opportunities to leverage something that's already out there that is readily available to a scientist or to a person who wants to tinker and figure out how exactly I could leverage that particular technology for an application. And so I'm going to talk about pretty much the Jitterbug system, which is a timing measurement system. And then I'm going to talk about sort of the applications that go with that. And I'm going to be leveraging Python as my main software. All right, so let's go to this first slide. There's a lot of different ways why one would care about timing. We know from 5G and 4G and the next 6G and what's out there that we're always wanting to know or try to get an idea of how far off we are with respect to time. And a lot of times we're looking at UTC as a reference. So with that, between the mobile user, the base station, there's different ways to actually account for your time. And I thought this was an excellent mapping of just some of the different errors that one would encounter when you're looking at timing. One is the time alignment error, one is the relative time error, and then there's the absolute time error. In a lot of cases, I tend to look at relative time error where I may, have a reference somewhere that's available within my system. And I just want to see how far off I am relative to that reference that's coming in. And that could be a GPS receiver. It could be another source of timing, maybe even being generated from a cesium clock. But at some point, I do have a reference that's available to me. And then I want to know within the network how far off I am in terms of being able to distribute that time. And that is the beginning of where I try to figure out what can I do, what measurement equipment is available to me to help me measure how far I am off in time. And so what I have to the right in this particular slide, three devices that one could use. There's your standard time interval counter that's available to you. This is a Keysight one. There's what they call the Time Spy from Brandywine, and that does, PPS. It does IRIG-B type of measurements on those timing signals. And then you have what you call the phase station that's located in the bottom right. That's from Microchip. That one allows you to do pretty accurate phase noise estimates associated with your timing equipment. So with those measurements, with those pieces of equipment, one could then go off and say, all right, I'm going to go some part in my network and I'm going to try to figure out how to either measure jitter or how to figure out how far off I am as far as the delay. Or I may want to figure out, what is the phase noise associated with this reference signal that I have. So most of the time when you're dealing with timing signals, there are pretty much, 3 to 4 basic signals that you're always looking for, or always looking at. One is the 1 PPS signal, pulse per second. One is called an IRIG-B measurement. That's a standard measurement that you find a lot of older equipment. The other is a 10 megahertz reference that's also available to you. In some cases, that could be either divided down or divided down into something like a 5 megahertz reference. But normally, you're either dealing with the frequency or you're dealing with the 1 PPS signal. And that's usually what you find in COTS type of GPS receivers. So let's look at some of the things that I was trying to explore here. When I was considering the timing measurement system, I wanted something that had sort of 3 design properties to it. One was simple operation. I wanted to be able to have a system that I could just give to somebody and say, hey, operate it. Here are a couple of buttons, not a lot of complicated menus you need to go through. I wanted to have flexible hardware that was available to me. When I say flexible hardware, I'm really talking about hardware that you can really get from Amazon, for example. And then there's flexible software. That again is availability. So in this case, I wanted to leverage Python because Python is readily available. You can easily install that on your Mac or your PC, or even Linux system. And with the flexible software, flexible hardware, and the simple operation, that allowed me to what I'm calling the jitterbug system. So I needed a neat name. I was already looking at jitter, and I said, by the way, let's just go ahead and figure out what this is. Maybe we can call it jitterbug. So this is always nice to add some fun things to projects. So with that, the software and the hardware, I started looking at, so what can I do within the software framework and what can I do within the hardware framework to keep things very simple. If you look at the middle of this slide where I'm talking about software capability, flexibility, one of the things that came to mind. So since I'm a tinkerer and I like to work on things in terms of I'm a maker, so I like to leverage technologies already out there. I thought CircuitPython would be a very interesting way to bring in some of the interfaces of a timing module within the Python framework. So I wanted to bring that in. Then also I wanted to leverage existing Python libraries that were already there as well. Now with that, I still needed an accurate way to measure time. No matter how you look at it, no matter how you want to develop your system, any of the software, hardware, I still always needed to have that basic way of measuring time as accurately as possible. This is where you bring in the Tucson Amateur Packet Radio guys. If you go to tapr.org, they have an excellent array of hardware that allows you to do very high precision timing measurements, and it's affordable. So that is, within the realm of the maker, allows you to say, yeah, I can leverage some of this technology and see if I can use it to maybe do some timing measurements on one of my systems. So that's where that sort of came into play, using the TAPR tick with the Python now allows me to give, to have to start with the framework. But with that, okay, I'm still not finished. I have the software I want to use. I have the, the high measurement interval that I have there. And on top of that, I needed a hardware platform. So this is where I brought in the PyTop 4. The PyTop 4 is pretty much a Raspberry Pi 4 that has the infrastructure around it such that you can, it already comes with the buttons. It has the battery built in, the rechargeable battery built in. Sort of all the things that you would have to try to buy on your own is already built in it, and it comes all in one. So that's great. So for a developer, you just want to be able to, take that, put that together very, very quickly. And now I'm able to rapidly build something and test it out in terms of what I'm calling the jitterbug system. So this next chart talks about the ecosystem of what jitterbug is about and what I was trying to do. The biggest thing here is that when it's all said and done, I'm trying to get accurate time precision measurements, but they're really based on a pulse per second. The TAPR tick that I was able to use in this project only operates on the taking measurements between PPS signals. So what does that mean? For someone that wants to measure all kinds of timing signals, I now need conversion modules that will allow me to get from a certain type of signal to the 1 PPS. And what I designed here in this particular case is what I said, oh, well, let's just leverage a lot of the modules um, that the TAPR group already had available. So in this case, if I have a 10 megahertz signal, I can purchase a 1 PPS divider that allows me to go from 10 megahertz to 1 PPS. And there's another device that you can buy that if you have iRig signals, you can convert from iRig to PPS as well. So I had the conversion process done. That's cool. Now, as I look at the tick, I'm trying to figure out, well, what are the other modules that I need? Well, for the operation of the time interval counter, you normally have a reference clock that you have to find, you have to generate. In this case, I said, well, I want to use something that's very inexpensive. So I ended up generating or creating a clock module that plugs in on top of the Pi. And what I'm doing with that clock module is I program that clock module using CircuitPython to say, give me 10 megahertz reference out. That then feeds into the tick. And then I ended up also having to add a real-time clock on that same module as well. So now with that module providing the 10 megahertz reference, now, howbeit, it's not a seasonal reference, it's not a very, very quality reference, but it's good enough to do relative time. And that's the key here. I can take differences within my time interval counter, use a very inexpensive clock to still get pretty good measurements when it comes to Allen deviations. So with that, that pretty much is, those are the components that I actually want to use to create the jitterbug system. Also, the OLED was important. I want to highlight that. There's a little screen that's on that jitterbug, or what's on the PyTop 4, that allows me to quickly assess whether or not when I'm making a measurement, is this seem right? Does this seem reasonable? And with that, with that in place, that allows me to at least have a feel for whether or not when I'm taking a measurement, do I need to do it again or not? And I'll talk a little bit about later on about what I'm doing with the data as I'm processing it. All right, so what did I end up doing? So again, being a tinkerer, right? I like to leverage what's already out there and see who's done what. I want to give a shout out or kudos, you want to call it that, to author Debbie J. Rowley. He was the first one I saw that really inspired me to want to build a timing device around a Raspberry Pi. He was the first one I saw that came out with, there's a paper you can find. It talks about high resolution time interval counter using the TPR, TAT2, and the tick modules. So he sort of gave me a template or an idea to show me how to develop everything around that. And he also used the Pi as well in his results. And it gave me a baseline for what could be done in terms of measuring the noise floor or understanding the stability and what is the minimum sensitivity that's available using the TAPR tick. And so with that, I went and I said, okay, let me just get a pretty much a Pelican case, get the PyTop 4, develop the module. I breadboarded out the module, with wires, basic things there, and I ended up with a decent system that I can at least start exploring and figuring out what can I do with respect to time. So in the display, what I'm doing is I'm wanting to see histograms and I want to see time series data. As I take the measurements between two different signals that are coming in through, which are going to be PPS signals. and then I display the jitter that's associated with that for some time interval. So now I have a basic baseline system that allows me to do a quick measurement. And one of the big things here is that I didn't want to use an oscilloscope to do these measurements. I wanted to be able to just take this as a device without having an oscilloscope or some other type of equipment and quickly be able to assess whether or not I'm getting the right jitter that I'm expecting to see. This is just one of the plots that was generated from Riley's paper. And I just wanted to show the phase data. And he was just pretty much saying that, yeah, with the floor of the tick that's there for the TPR, you can roughly get down to, pretty much 60, 70 picoseconds in terms of making the measurements associated with the jitter. And then if you look at the actual Allen deviation of that, you can see that roughly at around a second, you're getting close to 77 picoseconds, and that ends up being sort of the limit. So this defines the limit, at least, of the sensitivity floor of what the tick can do. And the question is now, well, what are the applications that will allow you to do this? Well, a lot of times, that's pretty good, 70 picoseconds. If you're looking at GPS receivers and you're looking at trying to figure out how close you are in terms of, two different kind of receivers of a different group that you're trying to use, that's plenty of sensitivity because a lot of times you're in the 10 nanoseconds and the 5 nanosecond range anyway. And that's what I'm going to talk about next. Is going to be the actual application of what I was trying to use it for. So with the general device, you're talking about the jitterbug. We have a way of capturing the data. We have a PyTop 4. We have the measurement equipment with the time interval counter. And again, the time interval counter, if I didn't mention before, very low cost device that you have available to you. Now, what are the applications? What can you use it for? Well, some of them here that I list out here very quickly. One is delay and jitter across the timing network, of course, and there's clock analysis. In general, Allen deviation, time interval error, time deviation, all those are different metrics in which you normally are wanting to consider in any type of timing application. So with this, I wanted to talk quickly and go through just the framework of the Python timing application that I was able to create around Jitterbug. And these blocks over here to the right are just going to be walkthroughs where I'm just going to walk through how I generate the 10 megahertz signal, what am I doing to set up the tick, and then what are the time interval measurements that I'm actually looking at, give you a couple examples of what that looks like, some plots, and then I'll summarize with at least some of the other applications that we're considering for this. All right, so this chart talks about the generation of the 10 megahertz that's needed by the tick in order to make a measurement of the jitter measurement. So primarily I'm using a SI5351 clock module. You can generate up to 3 clocks. In this case, I'm just using it to generate one 10 megahertz clock. What's neat about this is that I'm leveraging Python as a framework within the Raspberry Pi, but then I'm using what they call Blinka, which is the CircuitPython interface driver to Python. Now, if you go to Adafruit.com, they're the ones that provided the drivers and understanding and the developers of the CircuitPython. CircuitPython pretty much allows you to take any hardware device that usually uses SPI, IC2, any other protocol, communication protocol, and allows you to interface those devices easily with a Raspberry Pi or another microcontroller. So this really is Python for microcontrollers is what I would call CircuitPython. So it's a very neat interface and a very neat application to develop things quickly within the microcontroller realm. So I thought I could leverage this, put this within a PyTop 4 construct, and then it will allow me to quickly make changes if I needed to the actual time clock circuit there. So that's the background for that, for at least generating the actual 10 megahertz. All right, after I generate the 10 megahertz, now it's a matter of me going off and saying, okay, I have CircuitPython working now. Let's figure out the Python SDK. What can I leverage? So what's neat about the PyTop 4 is that it already comes with the drivers and interfaces that's needed to, of course, read the controls off the buttons and being able to leverage that API. So I took that API, already had it in there, leveraged that within my Python application, and I'm off to the races in terms of being able to at least come up with a simple interface to select through the different images that will come after I do my jitter measurements. One thing I guess I was making note here is that for the TAPR tick, there are a lot of different modes you can set this in. The mode that I'm using is a time interval mode where I'm taking the difference between the two ports. I have two PPS signals that are coming in from two different timing sources, and I'm making a delta measurement. And again, I want to emphasize that's how I'm able to get away with a very inexpensive clock to make my measurements because it's going to be relative to that clock. And both high accurate signals that are coming in through the other two ports of the tick, it pretty much cancels that out. So I can only focus in on the differences between the signals that I care about. So that's a nice trick, at least in this case, to be able to keep it very, very low cost. Okay, so once I was able to get everything working, I got the serial report going, I had the Python now running. What was my measurement that I wanted to do? So going back to the application, I wanted to see how close I had two GNSS receivers. How close are they in terms of the jitter measurement? So once you get a lock for a GNSS receiver, it's going to be within UTC a certain amount of nanoseconds. So what you can do in this kind of application is if I have a distributed set of GNSS receivers and I want to see how well I can leverage their, or how aligned are their clocks with respect to jitter, I can make these kind of measurements with the jitterbug system. So here I would just take the PPS that's coming out of the GNSS receiver, and even if you had a 10 meg, you could do a divider and actually get that down to 1 PPS, and those are the inputs that go into my time interval counter. And then at that point, I'm just making delay measurements, and I'm tracking those delay measurements over time. And so I can do that as long as I like, and then at some point, if I want to do additional analysis, this is where the Allen deviation comes into play in terms of the differences. So with that, the time application processing flow, this gives you an idea at least of what is going on with respect to the process. And so first I'm bringing in these TIE, what I'm calling time interval error measurements, filtering those out, and then I'm doing some type of statistics on it. And in this case, I'm using NumPy. It's already there within the Python library. And then I do basic jitter and delay measurement analysis on that data. Now, what I also wanted to provide here is a way to now leverage what's already out in the community in terms of what's already existing in terms of Python libraries. I wanted to call out here Allen tools. That's something that you can import in from Python. You can load that library in, and that gives you all the tools to do Allen deviation of the data that's coming in from the TIE measurements. So in addition to doing the basic jitter and delay measurements that are going to show up on the screen, I can post-process that data later on after I get a quick look and use the actual Allen tools at that point. So that gives you, again, some additional flexibility in terms of how to use the system itself. All right, so let's talk about some of the measurements and what we're able to do here. This is just an overall view of what you see both on the screen within the jitterbug system when you set your time for the measurements that you actually want to have here. The way the menu I have set up, I found out that 30, 60 seconds all the way up to 12 hours. That's a good range because that usually gives you the time. 30 seconds gives me a quick way to just give me a quick analysis of what I'm getting in terms of the jitter, whether or not I'm thinking I'm in the right ballpark or whether or not the clock is warmed up enough. And then the 8 hours, of course, is once I have the stability, I can just let it run overnight and see how well things are running in terms of stability between the two GPS receivers. This is now the output that I wanted to at least show a comparison. So normally when you're dealing with TIE analysis, you want to find or have an understanding of what is relative, or meaning what is a good reference to understand what you're looking at when you start looking at Allen deviation kind of plots. So this plot here is just a plot that I was able to download from Microsemi. It gives you a baseline measurement, at least of Allen deviation with respect to the GPS ADAV reference and where you expect to be as you are increasing and averaging your time series over time. And with that GPS, you can see where that is in terms of the plot there. But you also get an idea of where some of your other more stable references are in terms of short-term reference. Now, one of the things you'll see, and I don't talk about it in this particular slide, but when you start dealing with GPSDOs, the power of the GPSDO in terms of the GPS distal oscillators, that for short-term, you can leverage things like a TCXO and OCXO to get very stable, very low island deviation measurements. And then long-term, this is where sort of the GPS signal kicks in. So you get a combination of both of those. In this case, I'm just showing separately what a GPS receiver would look like in terms of jitter and island deviation analysis, and then what you could get if you had a CGM or had any other type of reference clock available to you. All right, so here's an example of using the Jitterbug system. I had an 8-hour collect between two GNSS receivers. The biggest thing here is that if I look at the 1 second tau, I'm roughly at about 8 nanoseconds for that. And that's pretty good, for a COTS off-the-shelf GNSS receiver. And then I'm looking at, how flat is that line going across from, the slope of that line going from 1 second out to the 8-hour collect. And if you look at that particular chart, you can see where I am relative to what I showed you earlier in terms of that noise floor, the measurement noise floor. I'm way above the measurement noise floor, for any kind of GNSS receiver stability. But notice that that slope of that line is indicating that I'm still within what I'm thinking I should get in terms of the Gaussianity of the error that's associated with those two clocks. And 8 nanoseconds again is reasonable for this. And then I did a 2-hour collect, right? I started off 8 hours. I wanted to reduce it down to 2 hours. And I just wanted to see to make sure that I was getting consistent numbers, especially at 1 second. I want to make sure that it should always be roughly around 8 nanoseconds or somewhere in that ballpark. Now, if you look at the chart to the left, or look at the images to the left, this was me sort of checking how the Allen tool was verifying what I was getting when I just did a quick collect as well. And so for this particular case, for the 8-hour collect, you can see that was around 8 nanoseconds, if the lower left corner of the actual Jitterbug system itself. So there's always a quick look that's available, and then there's always the additional analysis that one could do using the Allen tools. So that helps when it comes to doing additional analysis and trying to figure out what's going on with your timing signals. And now in this case, I wanted to look at holdover, where I wanted to disconnect my GPS receiver after 100 some seconds just to see whether or not it was behaving like it should. So I should start going off. I'm not going to have the long-term stability anymore. Now I'm basically leveraging what's internal, my internal clock that's within my GNSS receiver, and this is typical of what you would see in terms of frequency stability plot for that GNSS receiver that's no longer being disciplined by the GPS signal. All right. So I wanted to quickly go through, at least give you an idea of at least some of the applications you could do with the Jitterbug system, give you some motivation of sort of why I created it, what I wanted to do with it, and then also provide you with some ways in which I was able to leverage things like CircuitPython, the standard Python libraries that you find on computers, as well as inexpensive COTS equipment that's out there, especially around time interval counters. Sometimes those are sort of hard to find. They're inexpensive. I think the TAPR device is pretty cool for what it provides you for the price point, and being able to to get down to at least 7 picoseconds in terms of the measurement floor is pretty good. Some of the things we're exploring now, beyond what I just showed you for the example for the two GNSS receivers, is we're interested. We do wireless ranging. So a lot of our capability is we have what we call an ENSCO timing communications and ranging device that allows you to wirelessly transfer time between nodes. And so we're looking to take this Jitterbug system, and now I can go and measure and see how far off are my two nodes between each other in terms of jitter and frequency reference, and get a better idea do I need to tweak anything else within the actual device itself. If I have two GNSS receivers that are located far away from each other, right, I can try to get an idea as best as I can. Hey, if I have one measurement over here and I have another jitter measurement over here, is it consistent? One of the things that's interesting is to see how jitter changes as you um, as you go in different environments, in different kind of collection environments. If you go to an urban environment, how does the jitter change versus where you have line of sight? Those are just little things in which one could explore with respect to using jitterbug system. But there's always some form of measuring with respect to some other device or some other thing that's actually out there. So what we're going to be actually at JNC 2023. If you never heard of that, it's a joint navigation conference, and that's coming up this summer. We're going to be actually exploring how to leverage a Raspberry Pi Pico to do timing measurements. And you won't get the 70 picoseconds that you would get from the TAPR tick, but you can at least get 9 to 10 nanosecond resolution. Sometimes that's good enough to just gauge for whether or not the signatures that you're looking for are going to be there from a timing system. So that's something that that I thought was needed. I would just share with the team here in terms of some of the things that we're trying to look at as well. So again, leveraging COTS. Can I leverage COTS? Use the COTS for what it's worth in terms of what it can provide. And then even though it may not be as good as what you get out there, there's always levels that you can try to figure out how to use something, and it still keeps it inexpensive, because the Raspberry Pi Pico is pretty inexpensive in terms of leveraging that as a timing device. All right, so in summary, I talked about CircuitPython, Python, how we're leveraging Allen tools for doing additional analysis on the tick measurements that are being made here. How we sort of put together in terms of this prototype system to go out and make measurements, leveraging what's already existing in terms of a PyTop 4. And one of the big things again is that TAPR tick 60 picosecond resolution. Pretty nice device for the price that you pay there. This is portable in that it's about 4-hour battery life, so you can easily charge it up. And the flexibility is there for the timing applications. I think is very important to at least see or know that the timing applications that are there, you can expand on this, right? This is just pretty much a hello world of timing in terms of a basic, like, what are the things you want to do? Well, you can do jitter analysis between two PPO signals, and then you can do some kind of noise floor analysis. That's where you start. And then from there, you can build upon your application and just continue to add to it to make it more, what you want it to be. But I thought this was a neat project, and yeah, that's the end of my presentation. Thank you again for having me.
Wonderful, thank you. So let's open the floor for some questions. Any questions?
Yeah, I have a question. Can you hear me, okay?
Yes.
Thanks for the presentation. I love seeing hacking together things with stuff off the shelf. I didn't know about that product that you mentioned, so that's really cool. Kind of a side question. You mentioned something about measuring time over wireless or wireless time distribution or something like that.
Yes.
Do you have a little more detail about what your design is like for that, or how that works?
Yes. So we currently have what we call these over to the right. We call them the sort of TCRDs. They are 5.8 gigahertz radios that allow you to do wireless time transfer. It's customized in that it's a custom algorithm that we're leveraging, but a lot of times when we're making those measurements, we're wanting to have inexpensive equipment that's available to us. And so for this kind of device, we've leveraged it to let's see, I want to figure out the application. We've leveraged it to, let's say I have two antennas that are available to me, and I'm wanting to beam steer. we've leveraged it such that we can at least show the feasibility of doing beamforming in a distributed way. So that's one of the applications that we've used that type of technology for. But mainly what it is two-way ranging. And for us, we're in the two-way ranging space. So we're always looking for ways to see how good we're doing when it comes to two-way ranging. And of course, when you figure out your time for two-way ranging, you can also get distance. And now you can see how you can use that for geolocation and other type of applications.
Are those devices available somewhere, or are they in-house design, in-house use, or?
Yeah, they're in-house. We're no longer at least making those. We're actually in the process of producing more of COTS versions because these are getting expensive, and we're noticing that a lot more people are wanting to leverage COTS when it comes to wireless and RF ranging. So we are going to be releasing a COTS version of this probably in the fall. So yeah, if you're interested, shoot me an email, and I can let know where we are in terms of the overall technology. But right now, it's a combination of COTS where we're looking to get at least 10 kilometers range. Then of course you can get it close in, probably and easily within 100 meters or 300 meters. But yeah, that's sort of the space that we're in right now, and we're looking to make special mods to it for different kind of applications. And of course, you can see now how the jitterbug system would fit into trying to figure out how well we're doing there.
Okay, great. Thank you.
You're
I
welcome.
have a question.
Yeah, go ahead, go ahead.
Yeah. So, have you looked at 5G, using your system in 5G?
Yeah, so I have not had a chance to actually monitor a 5G network with the system yet. I know I showed it early on, the concept of where you would put it, within the network or trying to use it within the network, but I have not had the opportunity to actually use it within a 5G network.
Do you have documentation about this system in ENSCO website?
Uh, I do not actually. This is what you guys are getting is actually like hot off the press, just developed.
Okay.
Yeah. This is like early prototype research here. So there's really no formal kind of documentation yet for it. But I could see us putting something out there. And actually, part of this forum was actually trying to get a feel for who is even interested in the concept and the project. Because a lot of times, you work on things, you're like, well, I don't know if anybody really wants to use something like this. But part of that is getting that feel, and if there seems to be an interest, then we could definitely work on some kind of documentation and letting people know about it.
Thank you.
You're welcome.
Also, I'm wondering, is it like, are you aiming to make this a product, or you want to have it open source, or like any comment on that?
Yeah, so I want it to be open source because again, I'm leveraging a lot of the great work that people have already done. I go back to what Riley was able to put together here, and it's pretty good. What my vision is, what I want to see is actually develop a platform that's very inexpensive, so other timing people can develop the Python applications, and then you can begin to share how people are leveraging those Python applications. So ideally, that's where I want to see it go. But right now, we haven't made any kind of decision on what we want to do with it. I just sort of developed it, came up with it, and said, "Hey, let's just share it with the community and see who likes
Yeah.
it." And then from there, we can try to figure out
Like
next steps.
like this board that you have, I think you call it TAPR, right? It's like a hat, I'm assuming, on a Due or on a Mega Arduino, right?
Yes, yeah. That board is made by the guys out at tapr.org. So you can go
Okay.
right there
That
now,
one's
look
open
at that.
source and free, right? I mean, open
That's open
source.
source and free. Yeah.
Yeah. Okay.
Yep. So if you
So,
wanted to build that board yourself, you could go there. Those guys again are pretty nice. And I think the
nice.
board, last time I looked at it, I mean it's no more than like $250.
So that's it. That's a board. That one includes the TDC, and then
Yes.
the rest is basically what you wrap around it, and then
Yes.
until you get to another world of open source, right? You're basically sitting in between.
Yes, it's like I'm combining the different worlds,
Yes.
and they may not know each other, right?
Yeah.
But that's sort of the power of open sources, where you can get
Yes.
different kind of open source people, and they don't even know. But
Yeah.
then you find that correlation, and you realize, like, wow, that's much powerful. So many things you can do, because now you bring in Circuit Python. That's a whole nother open source world within the Adafruit.com community. Now you bring in what's already there in terms of Circuit Python. Let me see if I can find that diagram. Yeah. So you have the world of Circuit Python, and you have Python, and then you have the guys at tapr.org that are generating their own tick. So yeah, that combination gives you that ecosystem that seems like it's just a lot of flexibility there for you.
So I don't know, did you have a chance to look at the time card, and let's say if we can somehow leverage some of the things on the time card with this?
I have not had a chance to actually look at that.
Okay. So that might, because that might be another interesting thing, like to do these things. Let's say, I mean, you don't have, let's say you can potentially put the time card also on a Raspberry Pi CM4, but let's say you put it on a PC, and then like it's a total different, let's say, game, I would say, at that point. And then you do things with whatever we have on the time card available, but then we can certainly, again, it's an FPGA design, so we can always modify things, add things, we don't have a TDC. Again, everything is on an FPGA, but I think there might be some potential for that. I don't know, Julian, what do you think?
Yeah, it's a different in measurement, right? The FPGA is 5 nanosecond resolution, so this is getting down into the TDC world, but we're working on some stuff that might get it more comparable to what this is.
Yeah. Any more questions?
Yeah, I have one question.
No, but go ahead.
Thanks a lot for your presentation. And I guess today's presentation, you mainly showed the Alan deviation and jitter measurement based on 1 PPS, but I mean, you can do that with the 10 megahertz. And what would be the sort of noise floor or floor of the Alan deviation with 10 megahertz?
Yeah, that's a great question. Actually, from the work that was done by Riley, that's actually with the 10 megahertz. He was doing a 10 megahertz, and he just did a divider, and he shows it over to the left. So that gives you at least an idea of what it would look like with the 10 megahertz, with that module. So yeah, I was doing PPS straight from the GPS, straight from the GNSS receivers, but this actually is a 10 megahertz reference measurement that's being provided here, where he took two 10 megahertz signals and was able to show what the floor was, and he's getting down to like 70 picoseconds in this. That's the first one here for the relative phase over time, and then he shows actual Allen deviation on it.
Yeah. So for this, I mean, I want to compare the 10 megahertz and our jitter is like 20 picosecond, 1 sigma, or like 10 to minus 11 at 1 second. So actually, I would like to have 1 digit more with this
Oh
performance.
yeah,
So
yeah. You're right. This won't get you there. Unfortunately, it won't. Yeah. I know the kind of measurement that you want in that, because when I'm looking at when I'm looking at Caesar measurements, I can't use this to get to that kind of precision. Yeah, it just doesn't go as low as at 70 picoseconds. Because at 1 second, you're right. You You want to try to get to 10 or 20, and it just won't do it. So it is limited in its application, but at least it gives you an idea where you know where your system should not be as worse, right? Like if you know your system is above at least 70 picoseconds, and you know you should be, under that, this will at least give you an idea that something's going wrong with your timing system.
So I mean, and this is done only with the time interval counter, I guess. So if you want to sort of leverage accuracy, you can always add DMTD to it with 10 megahertz, not with 1 PPS maybe, but with 10 megahertz, you can do
Right.
DMTD. So you can always, if somebody needs it, you can always go there, I believe.
Right.
Thank
Right.
you.
Now, the one thing I didn't mention, there's some research out there where people are using software-defined radios and they're turning those into high precision measurement systems as well. So that would be the other route that you would go. Once this is not sufficient and you still want to use COTS, there's a great paper out there where someone was actually showing that result as well. And they were getting closer to what you were looking at in terms of the 20 picosecond range with that. Yep.
Any more questions? In general, with like software-defined radio, like you are always in steady state rather than in transients. So wouldn't that be an issue? I mean, that's just like speaking general. Isn't that the case?
Well, but remember with SDR, right? You still are, in essence, you have control over your. Well, okay, I'll say this: you should have control over the reference that you leverage within your SDR. That
Yeah.
is a caveat, it's a catch-22 there. When I say they were leveraging the SDR, there was some control that they had available to their reference clock as well.
Yes.
But mainly it was streaming and capturing the raw signal and doing post-processing. So if there was some issues, you could compensate for it within the algorithm on the back end. And it wasn't a real-time system that they had. It was really a post-processing system. So I would suggest that, yeah, you could get away with compensating post, but coming up with the real-time, it will be a little bit more tricky to actually do that.
And also, if you basically, this is maybe I can rephrase it this way. Is there a wish list you have, let's say, in terms of, again, hardware available to you, like like the COTS, basically, that will give you, let's say, more things, like, for example, something that allows you to do timestamps, or something that allows you to do, I don't know, like more, again, what you mentioned also there, that gives you a certain limitation, something with higher precision, like a clock generator or something, because like analog device, for example, which one was it, Julian, the chip?
9546.
Yeah, 8095 46, yes?
Yeah, yeah.
Yeah. So that one, like, for example, has a bunch of these, like, say, features, but I mean, it doesn't have the TDC that takes you 20 picosecond. I know, but the precision of that one is also high, I guess,
It does.
right?
It does. It's like
It does.
11 picoseconds something.
Yeah, like, let's say if you have something like that available, again, this is speaking from community, from community side. If we make, let's say, something like that, a shield or something, would that give you a boost?
Oh yeah. Anytime you can get the precision and you keep it within the cost is doable, right? That's something that I'm always looking at, and we're always looking at as a company to leverage, because again, we're looking for applications and ways to quickly develop those things that are already there. And if that precision is already there, what it does, it gives us the what I call it, it gives us the libraries, right? It gives us the flexibility to say, you give me your application, and then I'll tell you what device will meet that particular application. And that's what it does. It opens the aperture for at least flexibility. Because some people, 10 nanoseconds is good enough. Some people, I need 20 picoseconds, or even lower. So having that flexibility is great. If there's a device that you guys have that is available, that you could put an Arduino or something else around it, right? That's always great to have. And I think the way I look at COTS is there's the flexibility of, the ultimate flexibility that sort of the SDR provides, and then there's the, low level flexibility that the FPGA provides to you. Between the low level FPGA and the SDR with ultimate flexibility, in between, I like to think of it as there's system on chip devices that allow you to approximately can get to what the SDR do, but it can't quite get there. And it may allow you to approximately get to where you want to get to the FPGA, but it's just enough to maybe get, some of the measurements that you care about. So there is this whole world of different options with devices and different things that I'm always exploring to figure out, does it fit the application that I'm seeking?
Like I think, let's say for the time card and time card 2, where we have 2 GNSS receivers, we're always looking for, let's say, methods to choose one over the other. And one of those, like we were hoping to get, is like basically measuring the ADEV for each one of the sources versus the atomic clock or versus whatever high stability oscillator you have on the time card.
Okay.
And there are different routes we can take for that. Like my initial, choice would be like, let's say if I do everything on the FPGA in logic, but then there is also this contrary to that, like, argument where, okay, great, let's do whatever is necessary, let's say TDCs or whatever on the FPGA, and then run everything on the host, because we're a PCIe card, right? So then do everything on the OS, and then from there you basically tell the time card, okay, choose this one or choose that one, things like this. I don't know if you're interested. Definitely the community will appreciate if you can help us with that. So
yeah, that's very cool. I mean, that gets back to what we normally do. So my background from Purdue, my research was with anti-jamming for GPS.
yes.
So I'm always looking at, I call it a fusion architecture or intelligent architectures that are able to select based on measurements that are coming in. So in a wireless environment, we're always interested in figuring out ways to either look at receive signal strength indicators, one, for GNSS, carrier to noise ratios. And in this case, what I was exploring here was jitter. Can I use jitter as that measurement to make a decision on whether or not I would choose it? So yeah, that's definitely an area that we're interested in, and we're always trying to figure out ways to build algorithms around around those concepts.
Yeah, Mark Fry is here. I don't know, Mark, if are you able to add something to it, because Mark does something similar as far as I know.
Yeah, we are currently not thinking about comparing the signals directly on the time card, but I think an application like this, like the Raspberry Pi base design, would be very handy for us to do our current evaluations for end-to-end synchronization. There it would be perfect for our setup. So I'm very much interested in this design, and also talking to my colleagues in how we could replicate something like that. So it's very useful for that.
Yeah, wonderful.
Very cool.
All right, any more questions? Okay, hearing none, then again, I'd like to thank the speaker again. Thank you very much, Will. And so in 2 weeks, we have this, we call it PTM night, a little bit different format. So basically, we'll have 4 speakers, and it's going to be exciting because, again, PTM, I think, deserves a little bit more attention. Yeah, this here, prototype timing measurements, also PTM. So what PTM stands for, again, precision time measurements, which the precision and prototype got changed here. All right, so we'll see you guys in 2 weeks.
Thank you again.
Bye, everyone.
Bye, thanks.